our molecular orbital theory yesterday. So if you go back in your notes, yesterday we talked about hybridizing to form sp3 orbitals for methane. And then we said that when you're hybridizing an orbital, you're also taking the two independent shapes and kind of merging them together into one unique hybrid shape. And so in the case of an sp3 orbital, you take the s orbital, which is like a sphere, and you take three equivalents of a p orbital, mix them together, and you get this kind of oblong balloon shape coming out of it. So the question is, what does this look like in three-dimensional space? So let's try to represent it. And I apologize, I'm not the greatest artist, but we'll do our best here. I'm going to first draw an axis going up and down, and then three-dimensionally I'm going to draw an axis going out like this, and then an axis like that. So we've got our three-dimensional coordinates. Can you guys see that all right? And then we've got one of these sp3 orbitals essentially going up like that, and it's got its little nubbin underneath. So that's an sp3 lobe sticking straight up. And then we need to have sp3 orbitals going in the tetrahedral shapes. So I'll draw a lobe going out like that and a little nub behind it. And then we've got another lobe sticking out here, a little nub over there. And then we've got another lobe in the back with the nub over there. So that's our three-dimensional orientation. Each of these blue balloon type shapes is going to be our sp3 orbital. So we can even label these and just write in, sp3, sp3, sp3. These are kind of arbitrary axes. I'm just trying to represent three-dimensional space. And in each of these sp3 orbitals, if we go back up and look, we've got one electron, right? If we look over there, one electron occupies each of the sp3 orbitals. So let's go back and draw those electrons in. So I'm going to draw one electron in this lobe, one electron in this lobe, one electron in this lobe, one electron in that lobe. And then our hydrogens, I'm going to draw those as green, can overlap, right? So I'll just draw in our hydrogen. And what orbital do the electrons in hydrogen occupy? An s orbital, right? So we just draw them as a sphere. Yep. It's kind of in between. Do you remember the model I brought in yesterday? Where we had a piece going straight up, and then one kind of sticking out, one pointed back, and one like that. It's occupying that three-dimensional position. Yeah, so if you get a model kit, it's a little bit easier. I'm not very good at drawing these three-dimensionally. I do my best. And each of these hydrogens that I drew also has an electron. So we can draw those in there. And now we've got what are called sigma bonds between the s orbital on hydrogen and the sp3 orbital. So let's go ahead and label these as well. Sigma, which oftentimes people draw using the Greek symbol. And a sigma bond is different than a pi bond, which we're going to cover later. A sigma bond is just a point-on interaction. Do you guys think the sigma bond can rotate? Yeah, so it's just a sphere interacting with a lobe, so it has free rotation. We'll see with pi bonds that that's not necessarily the case with them. Are there any questions about the 3D picture? If you go through your textbook, it does a better job of representing them spatially because they do shading and stuff that I'm not capable of doing. Let's try some examples with double and triple bonds, though.
That's the CH4, right?
Yes, this is CH4. So that was the example we kind of stopped on yesterday. I was hoping we would have time to go through it, but we ran out. Okay, so let's try a different one. And I'm going to stick with hydrocarbons. Let's try C2H4. So this is ethylene. It's the monomer for most of the plastics that we use today. So if you guys look at the bottom of your water bottles, it usually says PE or HDPE. That stands for polyethylene, high density polyethylene. But let's first draw the Lewis structure for C2H4. And I'm going to have you guys try to help me with some errors here. Is that good? Yeah, we don't have an octet. We don't have the correct number of valence electrons for all of our atoms. So there should be a double bond right here. What are the approximate angles between each of these atoms? 120. So if you use your Vesper sheet, you can see that for the central atom carbon here, it's going to be about 120, if not exactly 120. What's the geometry for that carbon? Yeah, trigonal planar. So we'll write that down. And is it SP, SP2, or SP3? SP2 hybridized, right? Because it's got a steric number of 3. So let's write that down. Yeah?
That's what's been confusing. I thought it was, I understand it's got the trigonal planar geometry, but it's a double bond, so wouldn't that still be, why is that not SP3 hybridized? It's still got 4 bonds.
That's a good point. So when we're looking at steric number, we're counting the number of bonded atoms, not the number of individual bonds. So in this case, if we're looking at this carbon, we've got 3 different atoms bonded to it in no lone pairs. That gives it a steric number of 3. Yeah. Okay, so we've got a lot of this figured out already. We've got sp2. So let's try to represent this using our orbital picture like we just did with methane. So we're going to represent it with 3-dimensional space. So what I'm going to do is draw a carbon atom here. And we've got an sp2 lobe. So let's draw an sp2 lobe. We've got one of them sticking out here. This is sp2. We've got another sp2 lobe that's kind of pointing back, so I'm going to draw that with the dash line. And then another one. Oh, try to shade this a little bit. Another one sticking out of the page. So this explains our trigonal planar geometry, right? So this sp2 lobe is pointed back into the board. This one's pointing towards our eyes. Yep.
So are the SP2 and the SP3 lobes the same shape? Do they still have that little thing on the end?
Oh, that's a good question. All right, so sp2 lobe compared to sp3, do you think it's going to be longer or shorter? Shorter. So P lobes are really long. They're the dumbbell shape. This one has less P character, so it's not going to be as long. It's going to be a little bit stubbier than an sp3 lobe. Does that make sense? Because we're trying to add together a sphere and a dumbbell shape. If we've got less dumbbell shape to it, it's going to be more sphere-like. It's going to be stubbier. Other than that, the shape looks very similar. It's just shorter and stubbier.
Okay, so it still has it's still got a smaller section that's like.
Yeah, exactly. I'm not going to draw those just because it's a pain. Yeah.
Okay,
All right, so these sp2 lobes each have an electron in them. And you guys remember with our example of borane, what else are we missing? Yeah, we're missing the hydrogen, but we're missing an orbital too. What orbital are we missing? P orbital, right? So there's also a p orbital. So let's do this p orbital in another color. All right. And for those of you that need a little bit of help with the orbital diagram, let's fill that in right below. So we've got our, yeah.
So what, is that just one carbon? Is that
Yeah, that's just one carbon right now. We're going to add in the other carbon here shortly. So we're just going atom by atom trying to build this up.
So those blue things are the H's?
These blue things are just the orbitals right now. They haven't bonded yet, but we'll show them bonding here shortly. So we've got our 1s And then we've got our sp2. We've got 3 of those.
Aren't we missing an electron? Shouldn't there be 4?
Yeah, we're going to add that in.
Okay.
So let's go through and add electrons to this. So we've got 1, 2, 3, 4, 5. And the 6th electron actually goes into this 2p orbital. So we need to make sure that we include that up here. All right, so if we go back up and we look at our Lewis dot structure, we've got ethylene. It's got 2 hydrogens bonded to it, so let's choose the outside 2 lobes. So what I'll do is do this one in black. This is our hydrogen. This is our hydrogen. And each of those hydrogens has an electron that can spin pair with the electron in those lobes. What do we call this bond again? Sigma bond. So the hydrogen s orbital is overlapping with the sp2 orbital on carbon, and it's forming a new sigma bond. All right. Now we need to account for the 2nd carbon in this molecule. So I'll put this carbon over here. And it has the same sp2 orbital. So basically I'm going to just clone what's on the carbon on the left and replicate it on the carbon on the right. So this has an sp2 orbital right there. Let me slide this carbon over. And it's got an sp2 orbital kind of pointed back, and then one that's sticking out. So this is sp2, sp2, and sp2. And each of these has 1 electron in them, so now we've got a sigma bond there, an unpaired electron there, an unpaired electron there, and we need to account for the p orbital. Okay?
Is the p orbital just that because of the double bonds?
Yeah, exactly. So in this case, we'll show this electron in this p orbital as being spin down. The cool thing is that these electrons can actually feel each other through space. And because they're aligned, they'll actually form a new bond because I don't do a very good job of showing it, but in space, these orbitals actually touch one another. So they're very close to one another. Yeah, right? They cuddle up. So they overlap, and these electrons get shared between the 2 adjacent p orbitals. Does anybody remember what this type of bond is called? Pi bond, right? So we've got a new pi bond over here. And you can use the symbol for pi if that's easier for you. And then last but not least, we've got these hydrogens. Shoot. Right here and right here. And these form sigma bonds with the sp2 lobes, right? Some people were asking me about pi bonds today, and they were saying, well, why doesn't the electron reside down here? It's kind of tricky. Electrons don't behave like we traditionally think of particles. They have wave-like nature, right? So in this case, an electron has equal probability of being on the top side of the lobe or on the bottom side of the lobe. So the true nature of the pi bond is that it can occur on either face and both faces simultaneously on each of these carbon atoms. That has to do with the weird, funky duality of electrons behaving both as waves and particles. So oftentimes when I draw a pi bond, I'll even draw it shared down here. Now, do you guys think these carbons can rotate now? No. If you have a point-on interaction, you can rotate and spin, but as soon as you're locked in with a pi bond, spinning becomes really, really difficult. What you can do that's kind of neat, and they actually have a section in your book, is you can bombard this with light and break one of these pi bonds, and this is actually how our vision works. So if you get photons hitting a double bond, it'll break the double bond and actually spin it around, and then it tells your brain, hey, you just saw a certain color. It's a really interesting phenomenon. So this is our 3-dimensional picture of ethylene. If you look on your problem of the day for tomorrow, I'm asking you to do a 3-dimensional picture for formaldehyde, but you want to do the same thing. You want to look at the carbon on formaldehyde, determine its geometry, determine its hybridization, and then go from there. For oxygen, you want to do the exact same thing, determine its hybridization and its geometry, and then try to draw out the lobes. If you guys get stuck, you're more than welcome to come talk to me or work with friends, though. All right, do you guys want to try a harder one?
Yes.
Yeah.
Quick question first. So the electrons, so the hydrogen electron is moving in its own orbital, but they overlap with the sp2 electron moving its orbital.
Yeah.
Okay.
And when they actually form the sigma bond, the shape of the s orbital changes a little bit. We're not going to get into it too much. If you go on and take more advanced chemistry, it forms more of a uniform, not clumpy shape. Yeah. Okay, so let's try another one. Let's try C2H2. This is acetylene. If any of you do welding, you're familiar with oxyacetylene tanks. You've got this hydrocarbon in there that's very, very flammable. So let's draw the Lewis structure, determine its geometry and its hybridization. Is that correct?
No.
No, it's a triple bond in this case. So now we've got an octet, we've got the correct number of valence electrons, so this looks good. All right, if we look at each of these carbon atoms, since they're identical, what's the geometry? Linear. What's the hybridization? SP. All right, so if we think about it, we've got one carbon here, and we've got an SP lobe sticking out over here. This one's even stubbier than sp2 because it has less p character. And we've got another sp lobe sticking out over here. Okay. And each of these has one electron in them. And are we done drawing orbitals coming off of carbon? Yeah, we're missing the two leftover p orbitals. So when we hybridize, we only used one of the three p orbitals. The two remaining p orbitals are still around. And these p orbitals have different orientations. One sticks directly up and down. And then the other one sticks out, so I'm going to shade it a little bit heavier. And then the other one kind of goes behind. Can you guys see that? Whoop. Oh, no. So one's sticking straight up, one's going in and out.
Oh, yeah.
Okay. So let's label this. We've got a p orbital here, and we've got one electron in each of these. So just like we did with the last one, let's draw the hybridized orbitals here. So we've got energy on one side. Our 1s orbital is there. We've got these sp orbitals where we combine one s and one p. And then we've got our remaining two p orbitals. So if we fill this up, we start from the bottom. Go 1, 2, 3, 4, 5, 6. So we've got one electron occupying each of these orbitals. I'm not showing the inner 1s orbital right now. We're just focusing on the valence orbitals. Okay, let's draw the hydrogen coming off of the end. So on one side of acetylene, you've got a hydrogen. Again, this is just in its own s orbital. Let me clean this up. And that hydrogen can form a new sigma bond with the sp orbital. Does that make sense? All right, so we've done one half of the molecule. The other carbon on the opposite side has the exact same hybridization and geometry, right? So we can draw this out. We can say, okay, this has a carbon that also contains an sp orbital. Let me see if I can Make this more symmetric. Oh, shoot. We've got a carbon there, and then our other sp orbital sticks out like that. So we've got sp, sp. Each of these has an electron, so we form a sigma bond there. And we've got an electron right there. What about our p orbitals? We got to include those, right? So again, we'll draw a p orbital. Shoot, I don't know what's going on. There we go. It doesn't like my hand. Got a p orbital sticking up. And then we've got another one kind of sticking out like this. Another one kind of going back. And these are our p orbitals. And just like on the other side, they each have their own electrons in them. Yeah?
The other one didn't have the thing sticking out. The P for the last one.
Mm-hmm.
It didn't have the P in the back.
Each of them has a p orbital sticking straight up and down and then going in and out.
In and out, yeah.
Yeah.
The other one didn't have the in and out one.
Yeah, on ethylene we only have one p orbital, so it can only be in one orientation. This one we actually have two distinct p orbitals, and they're each going in a different direction.
Oh, okay.
Yeah. Okay, let's include our hydrogen on one side. So we've got a hydrogen there that can form a sigma bond. And then, if we look at this, the p orbitals again are aligned. So let's look at the p orbital sticking straight up and down. You guys see how they have, oh, I should draw the electron pointing spin down, sorry. Okay, now they're opposite spin. Since they're aligned, and through space they can feel one another, again they're going to form one of these pi bonds. So you can form a pi bond right there. And then this orbital that's sticking in and out of the board, pointing towards you and away from you, this can also form a pi bond. This is what accounts for the triple bond, right? Oops. So a triple bond is really two pi bonds and a sigma bond. You've got a sigma bond that's a point-on interaction, and then you've got two orthogonal pi bonds that are holding this molecule together. Can this rotate between the carbons? This is really rigid because now you've got two pi bonds locking it into conformation. All right, another tricky question. If we're looking at acetylene, which is a carbon-carbon triple bond, will it be longer or shorter than a carbon-carbon double bond? Shorter. And the reason behind that is that we've got two sp lobes overlapping. We said that they have less p character, more s character. They're stubby. That means that this bond's going to get even shorter. So if we're trying to order bond length, a carbon-carbon single bond is the longest, followed by a carbon-carbon double bond, and then a carbon-carbon triple bond. And we can rationalize that using orbital hybridization. Yep.
So there are three sigma bonds?
Yeah, if we look at the molecule, we've got a sigma bond between each of the carbons, and then a sigma bond between the carbon and hydrogen on each side. So yes, there are three. Let's actually write this all down, just to be thorough. Yep.
If the green means the orbital one, why we have four p orbitals?
Each carbon has two p orbitals coming off of it that were left over, right? So we hybridized each carbon, and there were two p orbitals that weren't hybridized. So on each of these carbons, we need to account for those unhybridized p orbitals.
So you still have to draw four orbitals and still include the sp orbital.
Yeah, you want to include all the orbitals for every single atom in the molecule.
Even if it's hybridized?
In this case, the hybridized we drew as blue, so it's not a true p orbital, it's not a true s orbital, it's actually 50% p-like, 50% s-like.
Yeah, I know. So, I mean, there's a two p orbital have been hybridized, so why you still draw four?
Because each carbon has two p orbitals, right? So this carbon has a p orbital sticking up and down, one in and out. This carbon also has a p orbital sticking up and down and in and out. So we have to account for both atoms' p orbitals. Is there a question in the back too?
Yeah, so is there discretion between which one you chose? Like, if you have chosen the P orbital at the back or the one at the bottom, or is it you just chose them so that they're opposite, like the one at the down and the one at the up?
Exactly. That's a really good question. So if you've got a p orbital sticking up and down versus in and out, can they form a pi bond? No. Through space, they can't feel one another. If they're both pointing in the same direction, meaning they're both parallel to one another, that's when you form a pi bond. And like I was saying before, that electron has equal probability of being on the top side or the bottom side of that pi bond on either side of that lobe. And in fact, it's in both positions at once, more or less. And so that's what forms a pi bond. Are your guys' heads swelling up with knowledge yet? Yeah. This can be a little mind-bending, I know. We're not going to spend a whole lot of time on molecular orbitals, but it helps to visualize what's occurring when pi bonds form, right? It's just two p orbitals that are adjacent to one another, sharing electrons. All right. Are there any questions with this stuff before we keep on going? Yeah?
How do you know if the bond lengths are getting closer or further?
That's a good question. So the question was, how do you know whether or not the bonds are getting shorter or longer? The more P-like character you have, meaning sp3 has 75% P character, that's going to be the longest because P's are dumbbell shaped. If you have sp, which has less P-like character, it's going to be stubbier and more S-like, which is a sphere. So they get shorter. Does that make sense? Let's even draw these so we can get an idea of what's going on. So let's do sp3. So we take one of these plus 3 P's. So when we hybridize all of these, essentially what you get is something that looks like that, right? If we go to sp2, we take our s orbital and only 2 p orbitals. The other p orbital is left behind. And then this gets a little bit shorter. So can you guys see how the balloon on the top is a little bit more oblong? It stretches out further. The one on the bottom is a little stubbier. And then if we go down to sp, you've got one s orbital and one p orbital. And these get super oblong. I'm not the best at doing art here. So in this case, this one has the longest. This one is our shortest. Does that make sense? So the top one has 75% P character, therefore it's more dumbbell shaped. Though SP1 is actually 50% S-shaped, so it's a lot stubbier. All right, let's go back to and take a look at these. If we're looking at a carbon-carbon triple bond, would you anticipate it being stronger or weaker than a carbon-carbon double bond? Stronger, because it's got a lot more electrons that are overlapping with one another. So this is also a key feature with a lot of these. Yeah?
Yeah, I was wondering if you could explain how you did the energy scale.
On the bottom?
Yeah.
This one? Okay. So let's go down. Oh, I'm going to slide this over and we'll show this hybridized on the right. This is good practice. All right, so carbon normally just has a 1s here, a 2s, and then we've got our 2 p's. And carbon has 1, 2, 3, 4, 5, 6 electrons. But in this case, we need to form 4 bonds, right? We need to form our triple bond on one side and our single bond on the other side. Right now, we only have 2 unpaired electrons. That's an indication that we need to hybridize because we've got a mismatch. So when we hybridize, what we're doing is hybridizing this 2s orbital and only one of the p orbitals, right? So these merge together to form our new sp set our 2p orbitals were left behind. And then, when we fill these with electrons, we fill the 1s completely full, and then our valence shell, we fill our sp and then our 2p, each with 1 electron. If we had an additional electron, it would fill that sp orbital, and we'd have a lone pair on one end.
Wait, I'm sorry, could you repeat one more time when you choose the first?
So we first fill our inner core electrons, our lowest energy level, but our valence electrons will fill each of those with 1 electron before we start doubling them up. Yeah. Does that make sense? Yeah, this can be tricky stuff, so try not to get super overwhelmed. All right, so now let's talk a little bit about non-bonding interactions between molecules. Does anybody remember the name for non-bonding interactions? What were they called? Shoot. Okay. Intramolecular forces. These are non-bonding interactions. So far, we've been talking about covalent bonds, but molecules interact in other ways besides just a true overlap of orbitals. So let's talk a little bit about types of bonds before we get into these. Yep. All right. So the first type that we've already covered would be something like ethane, where we've got all single bonds. And we said that this is a covalent bond. Right? We also saw one yesterday that was also covalent, but a little bit different. This still contains covalent bonds, but what's special about this compared to ethane? It's got the lone pairs. What's unique about oxygen compared to carbon? Super electronegative. So on this side, carbon is relatively non-electronegative, same with hydrogen. They're not tugging on electrons too much. On the other side, it's still covalent, but now we've got some unequal sharing of electrons occurring. So both of these can be considered covalent. What about this one? Ionic, right? So we've got covalent on one extreme. We've got ionic on the other, and then we've got something in the middle called polar covalent. Each of these interacts with one another differently. And a lot of people say, well, how do I know if something's polar covalent, or how do I know if something's ionic versus polar covalent? And we can actually determine this by using an electronegativity table. Do you guys remember that from general chemistry? If you go online and Google electronegativity table or open it up in your textbook, they're defined values for atoms, right? What's the most electronegative element on the periodic table? Fluorine. So typically the most electronegative elements are going to be considered fluorine, oxygen, and nitrogen. The halogens, so fluorine, chlorine, bromine, are also relatively electronegative as well. So let's consider each of these, and we'll say a non-polar covalent molecule has a difference in electronegativity of less than 0.5. The electrons that are shared in those covalent bonds are more or less shared equally. So in this case, the difference in electronegativity between carbon and hydrogen is 0.4. It's still a little bit polar, but not enough to be considered a serious thing. If we look at polar covalent molecules, these have a difference in electronegativity of 0.5 to 1.7. So in this case, the difference in electronegativity between carbon and oxygen is about 1.0. So this is a significant imbalance in charge density, right? If we look at ionic bonds, these have a difference in electronegativity of, more than 1.7. So in this case, are the electrons even being shared anymore? No. In fact, there's such a big difference in electronegativity that chlorine steals that electron from sodium. Chlorine becomes negatively charged and sodium becomes positively charged. So we're going to talk quite a bit about these forces that hold these molecules together. But let's talk a little bit more about differences in electronegativity. A difference in electronegativity results in something called a dipole. So let's take a look at the example that I just had. You don't even need to know, let me actually kink this a little bit. You don't even need to know the exact values to be able to predict a dipole. So in this case, what's the most electronegative atom in this molecule? Oxygen. So it's going to be the electron hog. It's going to be the one tugging on electrons. So the way organic chemists or chemists in general like to show this is they say, all right, it's going to be tugging on that electron density in that covalent bond between carbon and oxygen. It's going to be tugging. What about between oxygen and hydrogen? Which one's going to win the tug of war? Oxygen. So it's also going to pull electron density away from that oxygen. Some people get confused by these arrows too, and they're like, well, your arrow's got a cross on one end. And there should be a cross on one end. And so when we draw these dipole arrows, you've got an arrowhead on one end, and you've got kind of a plus sign on the other end. So what this means is that this side is more negative, meaning it has more electron density, and the left-hand side is more positive. There's also another way of writing these, so I'm going to copy this down over here. Some people don't like drawing the arrows. They prefer to use symbols. And if you are going to represent this symbolically, what you do is you just write a delta negative on that oxygen, indicating that it has a partial negative charge. And then you have a delta positive over here and a delta positive over here. That just shows you symbolically where the electron density lies. In this case, does a hydrogen have a true positive charge? No, it's just a partial positive. It's not a complete positive. So delta plus and delta minus are used quite a bit in organic chemistry.
Is there one that you prefer versus the other?
No, I honestly switch between them. One cool thing is with the arrows is you can think about these arrows as being like vectors, right? How many of you guys have heard of vectors before? So most of you are familiar with that in math. If you've got vectors pointing in opposite directions, what happens? They cancel out. This is the exact same thing with dipole interactions, right? If you've got vectors pointing in equal and opposite directions, they can cancel one another out. If you've got one only pointing in one direction and nothing counterbouncing it, that means that there's a net imbalance of electron density, and you end up with a net dipole. So let's take a look at the one on the left, and we'll draw a net dipole symbol in blue. And in essence, what happens is you get a net dipole pointing in that up direction. So some people, when they draw this, will just draw the net dipole or the individual dipoles. I'll leave that up to you guys. But this will help you with the problem of the day. All right, when we come back tomorrow, we're going to focus on intermolecular forces more. But if you guys have questions, feel free to let me know.